Hello everyone. So today's tutorial we will talk about reinforcement learning. So first I will present you some of basic deep learning reinforcement methods, and then we will emphasize on implementation of actor-critic algorithm. So you will understand why actually we use this strategy, and let's start. So. Deep Q learning, actually, it's one of the basics reinforcement learning algorithms. So in the Q learning function, we use Q tables. Then we actually can create some heat map. So in this, it's actually have for each iteration, we have for each state, we have in this table we have Q table. Okay, so this is actual table that consists of our of all our states and actions. Okay, so this strategy is very suitable for mid-range and small problems where you have actually finite steps and of your exploration. Okay, but when you're talking about when you have large scale problem, it's actually not feasible to have a Q table for all of your stage. Actually, if you have think about games that have a few thousands of levels, so actually you need to replicate this table for each each level to have all the options that all your strategy in each level. Okay, so this is strategy for this is very simple strategy. So in this strategy we have a state and action Q table that actually we learn our value iterations, and then we for each state we maximize our policy. So in Q learning, we are talking about deep Q learning. So let's revise what is Q learning update strategy. So new Q value for current state is actually your current Q value, and plus your learning rate. And here we have actually some of our reward. It's actually our. Okay, I can do it. So it's our reward function. Okay, so it's actually what reward for each action that you have. Okay, and then we placing our discount rate. So discount rate is our it's a parameter of how we believe in our future steps. Okay, so it's parameter from 0 to 1, and then we maximize the expect future reward given for actually it's our we summing our expectation new reward minus our current reward. Okay, so it's actually a simple algorithm that works very good for a small small scale problems. Okay, but here it's actually this Q learning algorithm. It's actually we calculate each of its steps. Okay, so now we are in deep learning course. So in our course we will approximate each of our actions. Okay, by neural network. Okay, so and this way we give more the algorithm will be more scalable, yeah, because we can use more faster approximator rather than making the calculations itself. Okay, so in our case we want to update our neural nets to reduce their. Okay, so the error is calculated by taking the difference between our okay, so we talked about it. So we have we have our change in weights. Okay, so it's our weights updating rule. Okay, so here we have, excuse me. Okay, so here we have learning rate alpha, and the underline green function is maximum possible Q value for the next state. Okay, and minus current predicted state as well as we seen before, and here we multiply it by gradient of our current predicted Q value. Okay, so there are two processes that happen in our algorithm. We sample our environment where we perform action and store the observed experience tuples in replay memory. Okay, so we select the small batch of our tuple, our state and action. Okay, and learn from it using gradient descent upstate. Okay, so again, this method, it's value-based method. Okay, so we calculate our reward. Okay, and update our weights or until we are getting score. Okay, so deep Q learning was very popular, and it used to solve a lot of simple games like backgammon and other games. Okay, so but his bottleneck and his pitfalls, it's that it's not scalable for large problems. Okay, so this is value-based simple algorithm. Of course, it's based on the Bellman equations, and now we will see reinforce with policy gradient. So policy gradient algorithm, it's policy based. It was value based. So in value based, we actually searching for our reward only, and policy gradient, it's based on policy. Okay, so we are looking for the best policy for given exploration. Okay, so we want to maximize our policy to getting the best policy star. It's actually best policy for given task, for given game. Okay, and we use Monte Carlo approximation for finding this pi star. Okay, this policy star. Of course, it's greedy algorithm. Okay, so it's have his bottlenecks as a greedy algorithm. So the time of it's converge very slow. Okay, great. So the first policy-based algorithms that we will talk about it's reinforced with policy gradients. Okay, so policy-based, instead of learning a value function, then tell us what is expected sum of rewards given in a state in action, we learn directly the policy function. Okay, but actually it will select actions without using a value function. Okay, so it actually means that we want to optimize our policy without thinking about the values, the explicit reward that we have in each state. Okay, why we want to use policy-based methods? Okay, so first we have two types of policy. A policy can be either deterministic or stochastic. Okay, so deterministic policy is the policy that actually it maps our state to our actions. Okay, so you give us a state and the function return an action to take. Okay, so for given state you have action that you have to take. Okay, that optimize it. Okay, so you have the best action for given state. You have the best action that you can take. So actually you have some state. Okay, so here our state. So our policy actually we want to take it. So the policy of for given state is A. Okay, so deterministic policy are used in deterministic environments. Okay, so most of the problems are deterministic. Okay, so if the problems are deterministic, so the environments where the action takes determine the outcome. Okay, so for instance, for example, when you play chess, you move your pawn from a2 to a3. Okay, so you're sure that your pawn will move to a3. Okay, so that's deterministic. Okay, so on the other hand, in stochastic policy, our outputs probability distribution over actions. Okay, so actually we measure our policy as a probability of taking some actions. Okay, so again, so if we want to optimize to calculate policy A for given state S, so it's actually the probability of taking the action at that state. Okay, rather than given some deterministic value. So, it's actually it's stochastic policy. Okay, so there are three main advantages of using policy gradients. Okay, first of all, it's convergence. Okay, why convergence? Why do you think it's that this algorithm converge faster than value-based policy? Jonathan, you have no. I asked why do you think that the policy gradient methods converge faster than value based than deep Q learning? Because
you have less of an error to propagate from the estimation of the Q value itself.
One of the possible answers, and the other answer is actually in the question. Okay, because it's policy gradients. Okay, so the gradient you actually you estimate your gradient itself. Okay, so yeah. So this problem is more suitable for convergence for machine learning algorithm. Okay, because value-based in value-based methods you have a lot of pitfalls that you can actually not converge at all. Okay, so here you actually have some assurances that you will converge. Okay, so yeah.
You know how Google, when they use Q learning for their AlphaGo algorithm, they make sure that they're not going to get stuck in some local minima that's going to ruin their training.
You ask what they report or what they actually do? I can't say it in YouTube. What they actually do, they run 100 experiments, and the best of them you see in the.
They just said, let's try a bunch of them.
Yeah.
One of them won't get stuck.
Look, most of the reinforcement learning algorithms are working are evaluated this way. Okay, most of the algorithms have a problem of local stacking. Okay, so it's not it's actually one of the problems that I have no time to talk with you, but most of the reinforcement problems actually are not better than random search. Okay. Yeah. Simple sample, taking samples of random, taking random exhaustive search. In most cases, it's give you better results than doing reinforcement learning action. Okay, but again, I'm talking about some large scale problem. Okay, with the small scale problem, you have no problem. You have you actually can have a benefit using the reinforcement learning. In so when you have a unlimited number of GPUs, you can try and then report one of the, cherry picking some results. Yeah. So what most of the big companies that have this unlimited research and this unlimited research servers are doing. Okay. Great. So we started from convergence. Okay, the problem with value-based methods that they can have a big oscillation while training. Okay, so this is because of the choice of action may change dramatically for an arbitrarily small change in estimated action value. Okay, so on the other hand, with the policy gradient, we just follow the gradient to find the best parameters because we actually working on on optimizing on getting best policy. Okay, so when we're searching directly to best policy, we can using optimization to reach it. Okay, great. So so actually this is our policy. Okay, so most of the here it's actually some local maxima, and here and the best parameters and actually give us some global maximum. But again, global maximum, it's very using reinforcement learning. It's very difficult to stay that we are getting back global maximum in our search.
Are we estimating the gradients and then applying our immediate estimation, or are we doing some sort of averaging over several estimations?
Of course, we are doing averaging. Yeah. Yeah. So as in other problems, we are first we calculate gradients and then we are averaging it. Okay, so it's actually more less time consuming, less time consuming methods. Okay, otherwise it will take a lot of time. Great. So we smooth actually update our policy for each step because we follow the gradient to find the best parameters that we guarantee to converge on the local maximum. Okay, it's actually the worst case and the global maximum the best case. So you have guarantees that in the in the worst case you have reached your local maximum. Okay, that this assurance you have no in Q learning algorithms value based. You have no such guarantees. Okay, great. The second okay, so the second advantage of using policy gradient algorithm is that the policy gradient are more effective in high dimensional action space. Again, it's this algorithm is more suitable for large scale problems because you have no you are not saving your you are not saving your values and actions for each table. Okay, you have no table. You are not saving your rewards for each actions. You are only optimize your policy. Okay, great. So when we when we're using continuous actions, so it's more you save more. So the problem with the deep learning is that their predictions assign a score for each possible action. Okay, so at each time given the current state. So but what if you have infinite possible actions? Again, it will doesn't work. For instance, with a self-driving car, okay, so for each state you have infinite choice. Yeah, so you can turning the wheel at it continues. You have infinite number of angles at infinite numbers of actually your angles that you have to turning your wheel. Okay, so and this is a problem because you have because here you have continuous exploration dimensionality. Okay, and you cannot using deep Q learning here at all, because your Q table will be infinite. You all realize the problematic why it's problem when your exploration is actually continuous. Yeah, if you have questions, please ask me. Yeah.
The signals that we use in order to estimate the gradients of the policy. So we don't have the Q and Q prime here that we can compare and derive the gradients from.
Yeah.
What are we actually?
I will show you. You are talking about actually the update rule. Yeah, I will show you the update rule. Yeah, I will show something. We will define some parameters that we will actually have on based on Bellman equations. So we will define it. Yeah, it's in a few seconds. Okay. Other questions? Great. So again, we have a problem: continuous sections, continuous dimension. We have continuous exploration here, so we can use Q values. So on the other hand, we can use policy methods. You are just adjust the parameters directly. So okay, so you only estimate the maximum directly at the maximum direction reward in each step. Okay. Okay. So it's some animation. So policy gradient go left. It's not problem. You have no in deep Q learning. You should have store a lot of data. Yeah. So you have store a lot of Q Q maps that will each of them should actually you need again the problem here is that we need to calculate the reward for each option. Yeah, here you don't need, in policy gradient you don't need to calculate your reward for each action before you're doing it. Okay, because you're only optimize your policy. So the gradient descent will optimize it. Okay.
Basically, update every action simultaneously because the policy is updated.
Yeah. Again, because the policy is updating, so you're updating the gradients. There you have actually in the previous you have not your policy is actually looking only your values. So you should have the all values. Otherwise, you cannot find you cannot converge because you need to find the root. Yeah. Great. Yeah. Yeah. So we talked about it. Great. So before we're going to start to define our policy search. A third advantage that the policy gradient can learn a stochastic policy, while the value function can't do it. Okay, so we have two consequences for this part. So one of these is we don't need to implement exploitation trade-offs because the stochastic policy allows us to the agent that finding our policy to explore the state space without taking some action, without measuring nothing, and this is because the output probability distribution over actions. Okay, so in the result, we handle the exploration trade-off without hard coding.
Exploration exploitation, mostly what we mean is we have a policy which we believe currently to be the best, but we don't necessarily take the optimal action.
Yeah.
Certain state, but we try to take other actions in order to improve our statistical estimation of which action is best.
Yes.
So the fact that we have a stochastic policy means the action is stochastic.
Yeah, the action, your action is stochastic. Okay. Okay, great. So so you have some flow. So yeah, okay. Okay. So policy search. So again, yeah, you have I have underlined it. So we have our policy pi that has a parameter theta. Okay, so this pi outputs probability distribution over actions. Okay, so it's we have the pi theta is actually probability to taking posterior A in term of S. Again, you saw this in other deep learning problems. So how we know if our policy is good or is giving us is giving us better reward? Okay, so how we can do it? Again, let's remember that the policy can be seen as an optimization problem. Okay, so we must find some parameter. We want to optimize something. It's learning to maximize a score function. Okay, so we define score function j in terms of theta, and then we want it's actually the expectation. Okay, so it's not, because it's probabilistic, it's stochastic, so we are taking it's expectation over of our policy pi over our rewards. Okay, so here our reward function. Okay, so why it's expectation and not the value itself? Because hi. Let's continue, guys. Okay, so I what I'm asking, why we're taking expectation? Because actually your measurement could be probabilities. Yeah. So you should take because we are talking about probabilities. So we want to maximize to optimize our expectations of each reward. Yeah. Why we are talking expectation and not the direct policy? No, direct on probability. But we are sampling, okay? We are sampling because we are as random variable. Yeah, we are sampling from and for optimize it. We should take expectation of it because it's random variable. Okay. So there are two steps. First, we measure the quality of policy with pi with policy score function j. Then we use our policy gradient ascent to find the best parameter theta that improves our pi. Okay, I'm why we use policy gradient ascent? Yeah, again, I will address and this issue to the other guys. We before that we saw optimizations that they're doing with gradient descent. Okay, so gradient descent is finding the minimum. Okay, here we want to maximize our policy. Okay, so we want to maximize policy. Maximization of policy. It's actually it's optimization in the opposite direction. Yeah, so we want to take actually gradient ascent for maximization our policy. Okay, great. So we want to maximize the sample of good actions. Okay, so is that clear? Great. So the second step we are taking policy gradient ascent. We are maximize the score function means finding the optimal policy. And to maximize the score function, we need to going against the direction of gradient descent. Great. So in gradient descent, we take the direction of the steepest decrease the function, and in gradient descent we are taking the maximization direction. Great. So the idea to find the gradient the gradient to the current policy pi that updates our parameters in the directions of the greatest increase and iterate. So first we have policy pi. Then we have we define the objective function j theta that we want to optimize. Then we defined our gradient. So our gradient will be, as you know, it's actually the j theta and our multiple the objection, and our update of theta is actually will be theta plus y plus. Yeah, in the updating rule of the weights, it's minus. Yeah, again, this is the plus because we are doing ascent, we are taking gradient ascent, and we have here it's actually our loss term. Yeah, so we have alpha is learning rate, and this is actually our the derivation of our loss functions. Yeah, true, great. So so we have missed the mass implementation. So please see the explanation in the class notes, or actually you or in other in a book. Okay, so let's conclude policy gradient scheme. We have policy gradient expectation over pi. We have policy function, and we have score function, and we want to update. We have update rule. Okay, so update rule is actually change in parameters theta and learning rate. Okay, so the policy gradient is telling us how we should shift the policy distribution, changing the parameters theta if we want to achieve highest score. Okay, so our tau is like a scalar value score. So if tau is if r is high, it means that on average we take actions that lead to higher rewards, and this is good. We want to push the probabilities of actions that we seen or not seen. Okay, so on the other hand, if tau is slow, it means that you need to we want to push the probabilities down. Okay, for turning the directions. Okay, so the policy gradient causes the parameters to move most in the direction that favors action that have highest return. Great. So we have seen two methods. One is deep Q learning. The other is reinforced with policy gradients. As we for conclusion, value based is more suitable for a small scale problem. Reinforce or Monte Carlo gradients make us opportunity to solve more complicated scenarios, but actually both of them have drawbacks. Okay, so both of them have drawbacks, and some hybrid algorithm can actually. His name is Actor Critic. He have actually benefits of both of these methods, and can solve bigger problem. Is suggesting, and we will present him now. So the problem with policy gradient. Okay, so policy gradient methods has big problem. When we are in situation of using Monte Carlo, waiting until the end of each episode to calculate the reward, we may conclude that if we have high reward, all actions we take were good. Okay, but it doesn't true. Okay, so if your final reward is good, okay, so it means that you some part of your actions were good, that part of the actions give you good reward, but part of the actions may have very bad reward. Okay, so as you can see here, so action number one was awesome and good, and then action number three was bad. Okay, so we don't want this that it will happen. We want that each of action will be good, because otherwise it's not it's suboptimal. Yeah, so this is one of the biggest problem. So we want this situation. We want that each of our action that that we take for given scenario were good. Okay, so as we can see in this example, even A3 was the best action. It's achieved good results. So as a consequence, to have an optimal policy, we need a lot of samples. So the problem that because we have some bad actions, we need more steps for getting a good policy. So actually, we can conclude that a policy gradient algorithm may need more time than desired. Okay. So what we want to do instead? Instead, we want to use actor-critic algorithm. So actor-critic algorithm is a model that better is a better score function. Instead of waiting until the end of the episode, as we do in Monte Carlo, we make an update and each step. So each given step that we take, we optimize it for we do update, and this way we optimize it. We find the maximum reward. So the policy update will be as the follows. So rather taking as we take in reinforce algorithm reward in a time t, we are taking a function q that have actually that composed of state and action of the current step. Okay.
Much more like dynamic programming, where we actually update our policy based on whether we move to a better state at this time step,
Yeah.
than waiting to see if the overall actions were.
Yeah. Yeah. We are not waiting until the end of actually calculating. Yeah. It's actually the best. It's fit to Bellman equations. Okay. So because we do an update at each time step, we can't use total reward. Okay, because we don't have total reward. Instead, we train our critic model to approximate the value function, okay, of each step. Okay, so this value function replaces the reward function in policy gradients that calculates the reward only in the end of the episode. So how it works? Okay, so let's see this, guys. So imagine you play a video game. Okay, so with a friend, okay, so you're actor and you are the actor and your friend is the critic. You want feedback from your friend. Okay, so you rotate the piece. Your friend is actually tell you if you did the good option or bad option. So you have actually actor is like your player, and you have critic. Critic is actually you have two nets. One of them is calculate your reward, and the other is actually telling you if you if you did the good choice or the bad choice, and if it's actually the bad choice, you fix it. Okay, so it's actor critic is like simultaneously you're doing you optimize both of them. Okay, so you have actor and you have critic. At the beginning, you don't know how to play. You try some action randomly, of course. The critics observe your action, provide your feedback, and you learn from this feedback. You update your policy, and be better playing for the next game. So, on the other hand, your friend critic will also update their own, provide feedback, so it can be better next time. So you update yourself, you're taking better action, and your critic actually updates himself too. So he will give you better critic. So it's simultaneously learning two-level learning algorithm. Okay, great. So the idea of factor critic is to have two neural networks. One is actually we estimate both our pi. Okay, so, pi is actually our policy given state, action, and theta. It's actually our parameters. And it's our actor, and we have our critic. So our critic is Q. It's a value function measure how good the detections are we. So you have this given state A, actions A, and parameters W. So you have look at this. Both of it's actually two neural networks. One of them is optimized theta. One of them is optimized W for given for the same for the same reward for the same action. Okay, so this both of them we are learning on the same parameters. Yeah, so only the theta and the weights are separate. It's actually how good are you, or how to how here it's actually give you the option to be better policy, and here to critique your better to for the next step. Yeah.
Basically, what you have is one network which, given a state and action, outputs an action. And
Yeah.
another network which, given an action and the state of the other, the first network outputs evaluation of how good that action was.
Yeah. How good the direction was? It's a critical work. Okay, so great. So because we have two models, actor and critic, so we must train. It means that we have two sets of weights. Okay, so theta again, it's our policy update. So here are theta. So we learned our function approximate estimate action value, and we have value update on our critic. So here it's actually the beta is the policy and the value have different learning rates, okay? And this is our TD error and gradient of our value function, okay? So let's see in this process. So at each time step we can we can take the current state for the environment and pass it into through the actor critic. So we are taking our our policy pi, our critic q, and we have optimized it. Okay, great. Okay, so our policy take the state output and action a theta, few minutes, and receive a new state st plus one. Okay, and the next reward rt1, our reward in time step t plus one. Great. So our policy takes the state outputs on action A and receives a new state, the next state, t plus 1 and reward t plus 1. So thanks to that, the critic computes the value, taking the actions and at the given state, and the actor updates its policy parameters weight using this q value. Okay, so here we see our actually the final theta update rule. So we have our learning rate and we want to minimize it. Great. So thanks that we our actor produce the next actions take action t plus 1 given the new state, and the critic then updates the value parameters. So we have value parameters. They are sharing from our action, our actor, and our critic. So we generate approximation value parameter by actor generate you his network generate you q value, and then this q value optimized by critic networks. Okay, so this algorithm it's actor critic. So there are other version of actor critical algorithms that it's asynchronous version. We don't use the difference between them that in the asynchronous version you have your gradient actually multiply your gradient and update it for asynchronously for each step. Okay, so you can take a few actions and policies in simultaneously, and this make your algorithm more actually faster. Okay, so DeepMind introduced the algorithm that their A3C or asynchronous version is faster for the given problem 4,000 times faster than the A actor critic version.
Basically, we check a few actions instead of one.
Yeah, you actually taking and you're parallel. You're distributing your actions. So you can take more actions because you have because neural network should actually you need network for calculate approximation of this action. You can do it. You can calculate it. You can inferencing it's deploying these networks in parallel. Okay, so for now we will finish.